So, very well. Welcome back, everybody. So, we have now the very final speaker of this wonderful series of conferences. So, it is really my pleasure to introduce Professor John Aaronson from Tel Aviv University, who speak about some infinite ergodic renewal theory. So, please, John.
Thank you. Thank the organizers for organizing the conference. It's really been great. So far, so good, and we're pretty close to the end. I want to thank you all for sticking around. And I have an announcement. If you had to catch the 4 o'clock flight, don't worry. Relax. You missed it. The second thing is that the last person out should switch off the light. Okay, so let's start. Everything I'm going to say is joint with Toru Serra. There are 2 papers. If I am not being understood very well, you can stop me. You should do that. But you could also download the preprints from Arxiv if the internet is still working. Okay, so I'm going to start off talking about some probability theory to introduce the basic result, and then I will give a slight general idea. The basic result is the sort of the motivation, and it's somewhat incomplete. Then there'll be a generalization to dynamical systems, which is maybe even less complete. And then afterwards, I'll get round to ergodic properties, related ergodic properties, infinite measure. And if there's any time left and anybody's still awake, we might even try some of the ideas of the proofs. But it's doubtful that I will prove anything from start to finish. So let's see if I got the right one. No. That one?
Touch the C.
Yeah, right.
Touch the green.
No. The white button. Okay, let's keep going with the white button. Yeah. But so I got to kick it. I have to kick it on the left-hand side. Yeah. Okay. So we start. So one of the ways to build a measure-preserving transformation, you start off with a base process. It's called a Kakutani skyscraper. So you have a base transformation. No, I'm not getting. Oh, there's a base transformation. It's a stationary process. So the first 3 things, omega mu tau, is a probability-preserving transformation, and I have a height function phi. It's a measurable function into the natural number. So this is a discrete version. And then you build a tower like that. So there you see the base transformation. And you see the tower, the graph of the tower function. And there are kind of instructions on how to do this, but this is for a very specific transformation, so you should ignore all that. This actually was originally called the Ohio State example, appeared in 1960 or something, but that's what it looks like. And that's the formula. So you take a subset of omega cross z. So the second coordinate is all the numbers between 0 and the height function minus 1. So what you've got, and what you do is you go up until you hit the roof, and then you jump down and go with the transformation tau. So it's a kind of, if we go back, can we go back? No, I can't go back. Yeah, no, I can't go back.
It's the button below.
The button below is to go back. Good. There we go. So we jump down. So what we've got, you see, all of these guys here are sort of periodic transformations. And I go up and I do a random periodic transformation. I finish the period, then I jump. Maybe I stay where I was and I do it again. Or maybe I go somewhere else and I change period. Okay. Yeah. It's all right, I'm getting there. So that's a skyscraper invented by Kakutani in 1943. Imperial Academy of Tokyo. Almost impossible to get the publication. So if you want to refer to something, that's the citation to give. So this is always conservative, meaning that with probability 1, almost every point in every measurable set comes back infinitely often to that set. The base is conservative because it has finite measure. And the tower has the whole transformation is conservative because you keep falling back to the base by definition. Nice model for all kinds of processes. We'll see renewal theory. I mean, there's this idea of light bulbs. You renew a light bulb, so there's an event on the base where you renew a light bulb. There have been more serious applications like earthquakes. Earthquake is a big bang, and then it recurs. You go up and you shoot out into up, and then you wait a long time for the next earthquake, or even other kinds of big bangs with the universe. But we don't know if the universe big bang is a recurrent event. This is not clear yet, so we don't know if we can apply that model. Okay, so more specific, there's a renewal process, and then you have a kind of, then I got a Bernoulli process, meaning that the phis are all independent random variables. The distribution of the phi is going to be f, probability on the natural numbers, and so I've got product measure. The renewal process is the skyscraper with the particular height, the height skyscraper associated to this base process. So according to Chung, this was first recognized, say, as a Markov shift by Chung in his 66 book. It's conservative ergodic, so conservative we know. Ergodic means that it's an irreducible process, meaning that you can go from any state to any other state, meaning that this will be ergodic, that the only shift invariant sets are trivial, either zero measure or full measure. So now we get to things technical. We talk about non-arithmetic distributions if the distribution is not concentrated on any non-trivial subgroup. And you call it aperiodic. Well, I've written down here some condition, but that means that it's not concentrated on a non-trivial coset. Okay? And then a renewal theorem says that if you're, so this F is called a lifetime distribution of the light bulb, right? We're changing light bulbs. We're mathematicians changing light bulbs, and you can count how many mathematicians it takes to change a light bulb. Yeah? So if the distribution is non-arithmetic, then you have this renewal theorem. So the result says that the tower, if F is non-arithmetic, then T is exact, meaning that there's a 0-1 law for the tail sigma algebra. So if it's exact, it's mixing. And so I will get this renewal theorem. So I've written it out. The probability that you renew at time n is, well, that's the sum of the probabilities that n was the kth renewal time. These are the sums of the renewal times. And this should converge to 1 over the reciprocal of the expectation. So this is an example of mixing on a measure-preserving transformation, which has a finite invariant measure, but it's not a probability, right? Because the measure of the space X is the expectation of phi. Okay? So that's why you get this funny formula. Okay, so this is very nice. And if the expectation is infinite, then the limit is 0. And maybe you didn't need to tell me that. Okay, so we look at what happens with infinite measures. So we look at renewal processes where the lifetime distribution have what has been called heavy tails, but I call them regularly varying tails. So a regularly varying function from the positive reals to itself, so that the f of lambda t divided by t, f of t tends to lambda to the p as t goes to infinity, and this should be for every lambda. And then you would call this regularly varying with index p, or p regularly varying. And I think later on there will be RV with dots, which will stand for random variable. Sorry about that. Okay, so for gamma between 0 and 1, we'll be interested in regular variation between 0 and 1. P gamma is all those probabilities where the truncation is regularly varying with index 1 minus gamma, okay? And then there's this, what do you call it, regularly varying Bible called Karamata's Tauberian theory. There's a nice book by Bingham, Teuchels, Goldie and Teuchels on this kind of thing, regular variation. So if you have f in P gamma, then the expected number of renewals up to time n, an, is going to be gamma regularly varying, and the distribution, equivalently, in this case, the distribution had regularly varying heavy tails. So in this case, it's lambda L of t divided by t, which is gamma regularly varying. So in fact, this is proportional to 1 over a of n, a of t. Okay? I think that's all the analysis we'll be doing. Okay, so then we get to strong renewal theorems. Yeah, okay, so the question arose. No. I'm not getting there, am I? So the question arose, can you differentiate the an? So remember, the sum of the renewal probabilities was an. And you would expect that the renewal probabilities, well, one thing that could be true, they could be the asymptotic derivative in this kind of way. So this question arose in the 60s, and this would be called the strong renewal theorem. So there's the lowest strong renewal theorem, which is true for non-arithmetic distributions with index between 0 and 1. This is the lowest strong renewal theorem. This will imply the Cesaro strong renewal theorem. And if you're lucky, then you get the strong renewal theorem. So this is always true in case gamma is bigger than 1/2. Or more recently, if an, this is Caravenadoni, they both did it separately but then published together. If an is bigger than some epsilon times root n. And then you get equivalence. So that's a good condition. We'll be using that condition. I don't think we're not going to be proving that. Okay, so here's an idea of how to prove that the lowest strong renewal theorem implies the Cesaro renewal theorem. Yeah. So what I had was this book thing from Karamata's Tauberian theorem was that so if my limit is bigger than the limit, first of all, the sequence should be bounded below. Secondly, it should be bigger than or equal to the projected limit on a set of density 0. And then weak Cesaro convergence, or Cesaro convergence to the limit, implies strong Cesaro convergence. So this is going to show that the lower strong renewal theorem implies the Cesaro renewal theorem, as we mentioned. And also, if I have, there really is an equivalence between density, because if I have U small, where U is regularly varying with, index between 0 and minus 1 and 0, then U small is the same as 0 density. Okay, so now we get into the statement of our theorem. So we have a renewal process corresponding to one of these f's. So if we look at that literary thing, we can elaborate that condition, and we can look at the conditional convergence of, so I'm going to let Sn, little sn, be the number of renewals up to time n. Okay? So that's the number of renewals. And now I'm going to look at the expectation of g of Sn over an, given that I'm renewing at time n. So this is a conditional expectation. Yeah? So that's what it looks like. So on the first page, the renewal theorem is essentially telling me that I got something going for me here. It's good. So, but now we want to do a functional version of this. So, functional version, instead of looking at the SNs, I define a random distribution function. So I'm looking at increasing right continuous functions on 0, 1, non-decreasing functions, and I define it by Cn of t is S at the floor of nt divided by an. Okay? So our result is that if f is gamma, it's got gamma heavy tails, and it's non-arithmetic, then there's some, there is some process, which means a random variable on this space of distribution functions. So, okay, I guess we should think about the distribution functions as equipped with the weak star topology on the continuous function, the dual of the continuous functions, which means that it's a locally compact space. And so far, but there's a choice of topologies. We'll get to other topologies later. So there's this process here, and you get convergence in density just under those assumptions to this limit, W gamma. So I'll tell you what W gamma, I mean, here it sort of looks as if it's dependent on the probability, but it's not. It's just dependent on gamma. So that should be, the statement should be reversed. So in addition, if I have the strong renewal theorem, the only thing that would, in fact, the only thing that prevents me from having full convergence is when G equals 1. And when G equals 1, this is the strong renewal theorem. Okay. So that's the first renewal theorem. So this...
Sorry, John, just a stupid question. That double barring what looks like conditional expectation is 1 bar. It's a conditional expectation. That right there.
Yeah, I'm doing, sorry, but...
No,
I had a twitch when I was typing the notes, and it comes out as a double bar. Sorry about that.
I don't know whether it means something more complicated or anything.
There's also a double bar on the expectation for symmetry.
Okay. Just to know.
I think it goes better in Japanese. So this thing is known as the tied-down Mittag-Leffler distribution process with index gamma. So this will come up later. So if you want, I mean, this is a special case of a tied-down Darling-Katz theorem, which we'll see later. Okay, so now we get to this is the bit where I try to extend to dynamical systems. So you have a result for independent random variables, and then people say, well, this has got to be right in a dynamical setting. So there's all kinds of dynamical systems where you have nice partitions or not, and you have spectral gap transfer operator with a spectral gap, and you can do perturbations and things like that. The simplest of which are subshifts of finite type with Gibbs measures and things like that. So Gibbs-Markov mat is a kind of subshift of finite type, but with countably many states. Simplest one possible, maybe. So anyway, we start with the 5-bit system. This is a definition of Schweiger's in number theory, I think, in the 60s. So I have a probability preserving transformation together with a partition, countable partition. So it should be a one-sided generator. So in normal circumstances, this will not be an invertible transformation, but it could be. And also, so on each partition set, I restrict, tau, the transformation tau is a non-singular transformation, invertible non-singular transformation between A and its image. So that should be true. So you can think about 2x mod 1. The partition there would be the left-hand, 0, 1 half, and 1 half 1. And each of the maps would take its interval onto the full interval. For example, you can also do Gauss transformation, I'm sure you're better at this than me. Okay, so this kind of thing is a 5-bit system. There's a natural topology there of alpha theta metric. So I choose a theta between 0 and 1. I define the alpha theta metric. D of xy should be theta to a certain power. Power is going to be, this power is t of xy, which is sometimes known as the separation time, the minimum number of the coordinate where they're not equal. So points which are close together, their expansions agree for a long time. And if it's the same point, then t is infinite and theta to the infinity is 0. So, I mean, it's not a proof, but it's an indication that I can get a metric out of that. But you can do that. If you get bored, you can prove that it's a metric. Okay, so then I have the idea of, I didn't write it here, but there's this idea of a locally Lipschitz function with respect to the partition, alpha theta Lipschitz if you want. So here's a function which is going to be Lipschitz on A. It's just Lipschitz. I mean, you say, okay, I mean, I look at fx minus fy. Lipschitz constant on A is fx minus fy divided by the distance. It's kind of cheating because you're essentially getting the same topology for every theta, so you should be talking about Holder functions, but it doesn't matter. Some people talk about Holder, some people talk about Lipschitz. And the reason I'm saying is I look back and I have papers where I say Holder and papers where I say Lipschitz. So that's my excuse. Gibbs-Markov, mixing fibered system. It's Markov, meaning that the image is a union of other partition elements. Big images, well, that's clear. There's a minimum size. And it has this Gibbs property. So there's a C and there's a theta where these local Lipschitz constants of all, so what am I doing? It's a big condition, it's a Gibbs condition. So I'm taking a cylinder of any length, so alpha n is the partition generated by expansions up to time n. I'm looking at the Radon-Nikodym derivative of the index branch of the relevant power. I'm looking at the log of the Radon-Nikodym derivative of that, and its Lipschitz constant on the image should be bounded by C. So that's a very strong condition. Kind of surprising when there are examples. There's Bernoulli shifts, of course, subshifts of finite type with Gibbs measures, but I cheated because that's where we got the idea from. There's Markov AFU map. So A means that there's an Adler condition of distortion. F means there are finitely many images, but you could think about piecewise onto, and uniformly expansion, so expanding. So C1 plus alpha map, which is say piecewise onto, uniformly expanding, and it has this distortion condition. I think the second derivative divided by the square of the first has to be uniformly bounded, just the first guy, and then you get it for all powers, which is the Gibbs condition. Gauss map, second power satisfies this. Okay. So now we go to the spectral gap for the transfer operator. So here's a definition of a transfer operator, the pre-dual of composition. So you get it by summing over you can calculate it explicitly for a fibered system. And for a Gibbs-Markov map, if I look at a Gibbs-Markov map with a parameter theta, it acts quasi-compactly on the Lipschitz functions with respect to this d alpha theta metric. So what does that mean? That, well, the projection operator is integral, and I converge exponentially to the integral with the error, exponential error times the Lipschitz null. And there's the Lipschitz null, regular Lipschitz null for you. In fact, you could put here L1, LP, whatever you want. Okay. So now Gibbs-Markov process is a random walk. We're going to do Gibbs-Markov we want to do renewal processes over Gibbs-Markov, so we need a height function. So I want a Gibbs-Markov process, and for the sake of simplicity, we want a Gibbs-Markov map and a function which is alpha measurable with respect to the partition. Associated random walk, that's the skew product. So you know what a skew product is, right? I mean, you shift on the first side, missed out on a bracket there, sorry. And then you add the function to the second coordinate. So we're going to call the Gibbs-Markov process non-arithmetic if the random walk is ergodic. Ergodic means that there are no shift invariant sets which are non-trivial. And we're going to call it aperiodic if it's exact. So, okay, you're going to tell me that the function is positive, and so it drifts off to plus infinity. So it's not conservative, so how can it be ergodic, right? But this is a non-invertible transformation. And so you can have transient random walks. The one-sided shifts can be ergodic. And this is what's going on. And in fact, if I had IIDs, then as soon as I have a non-arithmetic distribution, the random walk will be ergodic. And if it's aperiodic, the random walk will be exact. So these definitions are equivalent to those for Bernoulli processes that we had before in that case. And there may be more familiar cohomology definitions of aperiodicity and non-arithmeticity for Gibbs-Markov processes, and this also works for them. Okay, so generalization that we have, if you have a non-arithmetic Gibbs-Markov process with distribution, the marginal distribution is in P gamma, then you have this, not light bulb, it's battery. The battery holds. The idea is that if I bang on that battery, then you can see the battery formula, but then I wouldn't be able to get back, so I'm not going to do that. So this is this conditional renewal theorem, the conditional tied-down Darling-Katz theorem. So when does the strong renewal theorem hold here? There's Melbourne-Terhesiu in 2012 that when the process is non-arithmetic and gamma is bigger than 1/2, gamma is less than 1/2, it doesn't have to be true. Also, when gamma is less than 1/2, there's a result, a Guesel earlier result, that if you have a smooth probability distribution, smooth in this sense, then it will be true as well. Okay, so now we're going to now we start off with the probability. I'm going to describe the limit. So you have to bear with me for the probability theory a bit. So now we're going to talk about D increasing R, which is distribution functions on 0R, same thing as 0, 1. And then we have on R plus. So here we thought about distribution functions of finite measures. Here we're going to talk about distribution functions of Radon measures on the positive reals, which means that they're finite on compact. They could be infinite measures, but they're finite measure to compact subsets, finite intervals. So for gamma between 0 and 1, the normalized gamma stable subordinator, so that's a random variable on increasing infinity, D increasing infinity. So you have stationary independent gamma stable increments. So stationary increments, I mean, the difference is eta s plus t minus eta s is the same distribution as eta s plus t plus u minus eta s plus u. That's stationary and shift. And the gamma stable increment, the gamma stable means this, that the Laplace transform is given by this formula. Okay? Okay, so if you take IIDs with heavy tails and you sum them up and you do the random distribution function, you get convergence to this stable subordinator. Mittag-Leffler distribution is the inverse of this. So if I look at the renewals, I should be getting the Mittag-Leffler distribution. So this is self-similar in this kind of way. And in fact, if you look at the moment generating function, it comes out as this power series, which is known as which is actually a Mittag-Leffler function, which was invented for, apparently, I was told, for different reasons by Mittag-Leffler. In fact, I was told at the Mittag-Leffler Institute when I mentioned this distribution that he was not a probabilist. Now, m of 1/2 is the local time at 0 of Brownian motion, if you know something. But if you don't know about Brownian motion local time, forget it. But that's the distribution. Now we have the tied down Mittag-Leffler distribution. So what do I do? Given a function in D up arrow infinity, I define this new function, which is, I'm going to look at the time t, and it's non-decreasing. This function is non-decreasing, so I go backwards, and maybe there's an interval where I didn't increase. So it's the infimum that I have the same value. Okay. So what I'm doing here, I'm defining this G of M gamma. Take the Mittag-Leffler process, take the smallest value or the largest value less than 1, where the Mittag-Leffler process achieved the value that it has at 1. Now I take the Mittag-Leffler process and take this evaluated at this function, this random variable times t, and divide by the random variable to the power gamma. So this would be the, if this was constant, this would have the same distribution as the Mittag-Leffler distribution because it's because of the self-similarity that we have here. Yeah. But I'm actually multiplying it by a random variable, which so I'm changing the distribution, and this is called the tied down Mittag-Leffler process. So in fact, I mean, omega of 1/2 is the, so they talk about a Brownian bridge. You can define Brownian motion and you condition it to be 0 at time 1. And the local time for that is this W1/2. Okay, so that's what we're talking about. So now we get into our results. So we did the finite dimensional distributions. So in fact, okay, so there are 3 limit theorems here. One is where you show that it's actually W the way we defined it. The second one was a bug in the proof, right? So we actually got the finite dimensional distributions, which I can go through. So what you can see, it's the kind of, yeah. So if I want to look at finite dimensional distributions, it makes sense to look at functions which depend on finitely many values. So you look at product functions like this. Okay, and these can be as smooth as you want or whatever, just as long as they generate. And then the expectation of GT of W gamma is, well, this splits up into a product of all the values you get for less than 1 and something containing equal to 1. So what's happening is that you get a usual kind of Mittag-Leffler, and then you wait a bit, look at the waiting time, and then you have another random variable, a special random variable, which is, this is the distribution. It's sort of like Mittag-Leffler, but not exactly. You're adding an extra coordinate there. So we call it W because the first paper we saw, it was a paper by Wendell in '64. And this D is a kind of waiting time, rather like the G, but you go forwards. The latest time where you stay the same as you were. Okay, never mind. I mean, this is just a description of the finite dimensional distributions. Then there's this anchor thing, which is a stochastic integral representation. So you can already see there are going to be 3 limit theorems here. One is for the definition, one's for the bug, and one's for the anchor. So if we get, maybe we're going to do I think maybe we'll have time for some of the anchor, but we won't have time for the others. Okay, so convergence in D, these spaces of distributions. So the 2 topologies. First topology is this vague topology. Weak star topology on the dual space of functions of continuous functions with compact support. So this would be finite measures if R is finite, and it would be radon measures if R is infinite. And then there's this strong Skorokhod topology, which is like uniform topology, but it's uniform topology where you allow yourself to displace by a Lipschitz perturbation. So you have a Lipschitz a bi-Lipschitz increasing map of 0R to 0R. So you measure how close that is to 1 by looking at the L infinity norm of the log of the derivative of that function. And then you look at the L infinity norm of the displacements. So that's what you get. So why do you do the displacement? If I just looked at L infinity, the space wouldn't be separable. This is Polish. Turns out, result of Skorokhod, that the Borel sigma algebras are the same, and they're both generated by finite evaluation. So in both cases, if you want to prove distributional convergence, you've got to prove convergence of finite dimensional distributions, which for the vague topology will be enough. But then if you want the Skorokhod topology, you've got to prove something called tightness or precompactness of your sequence, which I'll mention. We don't have to worry about that here. except for one place. If we get there, I'll mention it.
Let me just stop you for a second. Evaluation of finitely many points. Is there?
Yeah.
Okay. So that's what whole sigma thing means.
What?
So I was expecting sort of ET1, ET2, ET3 or something. That on the last, yeah.
Which one?
Second to last line.
Yeah. This one?
Yeah.
Or this one?
Go to the right, go to the right, to the right.
Yeah.
There.
Yeah, sigma accountably many points. I mean, you take in the sigma algebra generated by those functions.
Yes.
So each set there, I think it'll be, there's this Borel construction or something that you go up to the first uncountable ordinal. So it's okay. So there is one thing that if you converge J1, then you converge distribution function. If you converge distribution function to a continuous limit, then you converge uniformly and hence J1, but not in general. So what does that mean? If I have a limit, a distributional limit, which is almost surely continuous, then distribution function convergence is the same as J1 convergence. So you could see that the Mittag-Leffler is what? Could you see it? Now you can see it. Mittag-Leffler and also the tied down, they're both almost surely continuous, so I don't have to worry about the topologies. But nevertheless, there is a point where I do have to worry about it. Okay, so now we get to the ergodic bits. So there's I have a conservative ergodic transformation. I call it pointwise dual ergodic if the transfer operator satisfies a pointwise ergodic theorem with respect to certain normalizing constants. So you call that the return sequence. So there's the transfer operator. So this condition was first used by Darling-Katz, or actually how do you say, a strengthening of it, that I actually have a set omega, a finite measure, that's finite measure, where this convergence is uniform for f equals the indicator of omega on the set omega. So that's a very strong condition. It happens, but it's not, we don't know if it's universal. I suspect that it's not, but I never managed to prove it. Never found a counterexample, never proved it. So our counterexample would be pointwise dual ergodic for which there's no Darling-Katz set. Okay, so for example, if you have a skyscraper over a Gibbs-Markov process, then you would get omega to be a Darling-Katz set, and the expected renewal time would be the return sequence. Okay, so this can never be invertible. This is never invertible when the measure is infinite. So there is an associated invertible property, for example, for the natural extension, weak rational ergodicity, which means that you have kind of weak convergence in this sense. So this is football. Football means that you look at the integrals of the number of visits to B up to time n, you integrate on A, and this is asymptotic to an times the product of the measure of the sets. This will never be for any two sets of finite measure, but there should be a dense hereditary ring. Hereditary ring, closed under finite unions, hereditary, also subsets, and dense means that you can approximate anything from within. Okay, so now we got the Darling-Katz theorem. Started with Darling-Katz. This was the, scalar version. I did a tweak, then Bingham did the scalar version not the scalar version, the functional version for Darling-Katz sets, and more recently, Owada-Smorodinsky did it for pointwise dual ergodic. So what do I get? Pointwise dual ergodic, and I have a gamma regularly varying return sequence. Take functions in L1. How am I doing for time? Almost finished?
No, you have 15 minutes.
15 minutes, great, yeah. Okay. So I do these functional interpolations here, and I get convergence to the Mittag-Leffler distribution, inverse of the subordinator times the integral of the function. Okay, so now we got the tied down ergodic properties. So as a consequence, just pointwise dual ergodic, So if I have a pointwise dual ergodic transformation with the right kind of return sequence, then if I look at these sums now, these are sort of, it's a kind of ergodic sum. It's a sort of rational ergodicity property with distributional limit. And then I'm going to get convergence to the product of the sets times the expectation of G of the tied down Mittag-Leffler distribution process. So this will be for A and B. This integral, these two sets have to be in the hereditary ring. And G should be in the, could be J1. It could be, all the continuous functions on D increasing for J1 if you want, because it's the continuous limit. So if in addition, it's weakly mixing, spectrally weakly mixing, and there's some set which has a Gibbs-Markov return time process. So that means that I induce, and then the induced transformation gets turned into a Gibbs-Markov process. Yeah? So this would be the return time function. Yeah? This is the induced transformation. Then I'm going to be getting strong Chisaro convergence here. Okay? So this is a kind of thing which I call conditional rational weak mixing. And, you know, that's without the G, but here is kind of specific in our regularly varying situation. If in addition, you have the strong renewal theorem, so that's over the Gibbs-Markov guy, then you have this kind of you have full convergence here. But you see here, I don't have any choice. I mean, I'm still with cylinder sets with respect to the partition. And the reason, well, one reason for that is that if I had a weakly wandering set, this would be impossible. It's impossible to do it for all sets. But what would be nice would be to, instead of just having it for indicators of nice sets, it would be good to have it for certain functions. So here's an example. You have interval examples. So these examples fit into Thaler's papers in 80 and 83, infinite measure preserving transformations. The same formula appeared in Liverani, Sorsol, and Vaienti in 99, but with p less than 1, so they had an invariant probability. But this gives you an infinite invariant measure. So here you're going to get that TP is conservative, and if you induce on 1/2 1, then you get a Gibbs-Markov return plane process. You get an invariant density which has a cusp of 1 over x to the p at 0. You get that, so consequently, you get that this is an exact pointwise dual ergodic measure preserving transformation with return sequence enter the 1 over p. So that means you have that this Mach operating system, which is the first one, with a pointwise dual ergodic, that's okay. And bananas also holds because it's weakly mixing, because it exact implies weakly mixing. Moreover, you have a smooth return time density. You can look at you can just look at that. And so you get by Guzel that this apple core holds. So what would be nice here is if I could take for the for apple core, I should be able to take A to be any interval bounded away from 0, and I should be able to take for my set anything about, you know, bounded variation of support bounded away from 0, but we don't know that. Okay, so now we get to the bits of proofs. So now I want to do Makos given anchor. So what I'm going to show is that if I'm pointwise dual ergodic and I take a limit, I get a limit, then I get this integral equation. So you see what's going on. So, okay, first I choose an epsilon between 0 and 1 and a continuous function. So this is going to be continuous with respect to J1, say. And I'm defining a new function, LG epsilon of C, which is going to be the integral from epsilon to 1 of G of delta. Did we say what delta was? Let's try and write. No.
White part.
Huh?
Right on the white part.
Well, I'll do gamma t, t gamma. Okay. There we go. Yeah. So that's that. I keep renormalizing that, and then I integrate that. Whoop.
Touch the green part.
There we go. Oh, can leave it. So the idea is that this should be, so this is now a new functional on these distribution functions. And you can check that this is continuous. This is continuous as a functional at every continuous function in D aparo 1. So therefore, if I look at this guy, LG epsilon Cn, first I can calculate it, and it looks like this ergodic sum. Okay? And secondly, by the Darling-Katz theorem, this converges to the integral with respect to the Mittag-Leffler process. So what have I got? I almost proved the theorem, not the theorem, but I proved it for two specific functions. For a specific function g and a set omega, right? So I want to carry on. So what do I have to do? I have to let epsilon tend to 0. So how can we let epsilon tend to 0? Well, I'm looking at the difference now. LG 0 minus LG epsilon of m, it's like the integral from 0 to epsilon. So this is bounded by the norm of g times the Mittag-Leffler measure of the interval 0 epsilon, which is that. But we know that it's self-similar. So it's epsilon to the gamma times the expectation of m gamma of 1, which was 1. So there we got that one. The second bit, I look at this guy. So I can forget about g, estimate g by the norm, and then I get the expected number of returns. So this is like a of n times epsilon. A of n times epsilon divided by an. It's a regularly varying function. So it's like epsilon to the gamma. The index is gamma. So everything's good. So that we get this special case of the theorem. And then you get the rest of it. Well, you get for all other sets in the hereditary ring using weak convergence. And then you change the function using the ratio ergodic theorem. You can use Egorov sets where it's uniform, and then you use weak convergence again. So that's anchor. We still got some time?
5 minutes.
5 minutes. Okay. Okay, so there's this, the other bits. I mean, there's, the finite dimensional distributions and bananas. Yeah, bananas was the strong Chisaro. So there's the main lemma here, that if T is weakly mixing and you have this Gibbs-Markov return time process, you have a functional version of the lowest strong renewal theorem, right? That's what it is here. Okay, so if we can do that, we get Appelkorf from the strong renewal theorem. There's kind of a way to do it, because if I have a G like this, which takes values between 0 and 1, I can look at 1 minus G, and 1 minus G will be a sum of the other guys. And so I can use the same thing twice and I get it. So that's quite a trivial remark, basically. And bananas will follow, even if I don't have SRT, using this Chisaro summation method that we have. Okay, so there's the main lemma, which is the uniform lower strong renewal theorem. Yeah, okay, so it's an operator version of all these. In order to do that, the main new technique was a periodic local limit theorem. So usually you have an aperiodic local limit theorem, but this is a periodic one. So you don't assume aperiodicity and you don't get the usual local limit theorem, you get it. So if you think about the simple random walk, you can only do the local limit theorem for even values, because you can't visit 0 at odd values. So that's the periodic thing. You take it into account that this kind of thing is going on. And then when you want to do that, we want to do this choo-choo train. What do we have to do? Yeah. So then we do this Garcia-Lamperti thing, and you get the sums involved, and they turn out to be Riemann sums for the correct integral, yeah? But the Riemann sums form, I mean, without the periodicity bit, they form a nice smooth measure on the integers. And so there's a uniform distribution which gives it to you. Okay. So the rest of it, I mean, this uses a distortion lemma, which is only for Gibbs-Markov, not for others. So that's why we're strict to Gibbs-Markov. Yeah, and the other thing, I guess, so if I want the finite dimensional distributions, I need that these, if you remember these D function and the G function, these are supposed to be continuous. I want to take them continuous under inversion. This is not true for distribution function convergence, but it is true for J1 convergence. In fact, so what's happened was, I mean, the convergence of the independent process and the Gibbs-Markov process to the stable subordinator in J1, this is known by Skorokhod for IIDs and Malta Tiran-Kaminska for Gibbs-Markov. And we don't know this for other processes. It's a mixing thing. You're using something called continued fraction mixing, which is basically psi mixing with a Renyi condition. Yeah? So then you get that everything goes continuously. So I guess we can do that now. Yeah, we can do the definition now. So we're looking at Gn to be the previous waiting time function. And then we get by the continuity, we get that delta Gn of gamma psi n converges in distribution to delta Gn of the Mittag-Leffler, which is the tied down Mittag-Leffler, okay? So then there's a kind of manipulation. I mean, it follows from this. I mean, we write down the expectation of GT of the tied down Mittag-Leffler. It's this limit. It's this sum. And then from what we proved before, it gives you the thing with the finite dimensional distribution. So that's it. Thanks for suffering. Thanks for listening.